Hi everyone, my name is Reem, and in our group project, we designed and simulated a MEMS-based thermal sensor using Simulink. In the first part, I'll briefly explain the working principle of the sensor and how the physical design is represented in a model. A MEMS thermal sensor works by measuring temperature-dependent voltage changes. So in our case, we are modeling a thermocouple type MEMS sensor where two dissimilar metal junctions generated a small voltage difference when the temperature changes. This voltage is extremely tiny, usually in the millivolt range, so the signal must be conditioned before it can be interpreted. But the basic idea is simple. A temperature input heats the sensor, this creates a voltage change across the thermocouple, the voltage is amplified, and finally it is converted into a readable temperature output and visualized in 3D. Now I'll pass it on to Chong to explain the Simulink block by block.
So in this section, I'll walk through the Simulink model and then explain the function of each main block. So we start on the left, where we have two types of signal. One is signal single, and the other one is continuous. Single only have 0 to 100 degree, but continuous has 0 to 100, then repeat continuously. So next we go to our Kelvin block. So the temperature signal is converted from Celsius to Kelvin. Then the temperature is set into the summing block, and which help generate the changing temperature profile over time. Next, our temperature passes into our thermocouple. This includes a voltage measuring block, the thermocouple terminals, and then the grounding. This correct reference point. After that, the millivolt gain block passes through into our main gain block and labeled as gain C. This converts millivolt reading into actual reading estimate. This result is set into scope C and then display C, which give us clean and readable temperature output. We also can use offset blocks to ensure the sensor is calibrating correctly, and offset tool is used to adjust raw signals. So our simulation starts from realistic baselines. So we feed the process temperature into MATLAB function block, temp to color, and convert temperature into RGB color value. This color is connected to VRSync 3D sphere, which change color based on temperature, giving us visual representation of normal behavior into signal conditioning, then becomes visualization. Now I pass it to the next presenter for our simulation.
Okay, so hi guys, my name is William and today I'll be talking about the 3D simulation of a thermal sensor. So first of all, the thermal file writes the thermal.wil, which is a simple 3D scene with a sphere whose color we control from Simulink via the VRSync. So looking at our Simulink model, here's a MATLAB function which is called temp to color that maps 0 to 100 Celsius. 0 Celsius indicates that the sphere is blue color, and then 100 Celsius indicates that the sphere is red color. Let's go back to our model. So right now I'll showcase our simulation. We have two types of input. So for our demo one, which is a single ramp, switch here, and then here's our scope. So looking at this first scope, the temperature is rising from 0 to 100 Celsius over the 10-second range. So if you look at our 3D sphere here and I press the play button, the sphere will show that it changes from blue to red, which means that the temperature rises from 0 to 100 Celsius. If I press the play button again and you look at the voltage display, it will show that the voltage is rising from 0 to 4.09 millivolt. So let's move on to the next demo 2. Click the switch and then change the stop time. D and then press the play button. So let's wait. So I'll switch the input to the sine block, which is a sine wave that oscillates between 0 to 100 Celsius continuously. So if you look at the scope here, it shows a sine wave. And then if you look at the 3D sphere here, press the play button, the sphere is changing from blue to red and then red to blue, which indicates that the temperature is changing from 0 to 100 and then from 100 to 0. So at the same time, if you look at our voltage display, it will change from 0 to 4.09 millivolt, and from then it will decrease back to 0, vice versa, which aligns with our temperature. So in conclusion, we have demonstrated both a single sweep and continuous input with temperature on the scope and a clear 3D color output that completes the required simulation and visualization. Thank you.